Hello, my name is Spencer Jensen, and this is my first round of interviewing at KTH for the open PhD position um, in generative modeling of conversational dynamics with Professor Eva Siki and Professor Gustav Hentek. And first of all, thank you for the opportunity for your consideration for this PhD program. I'm really looking forward to furthering my education and really growing in my career. A little bit about me. I'm from Washington State in the United States, and I have my bachelor's and master's in information systems. And so I was a software engineer for a year and a half at Rosetta Stone. And at Rosetta Stone, I really got involved and interested in language technology. I was doing language certification software and really got interested in some of the ASR and language processing technologies that we were using. And so I actually applied to the MSc of Speech and Language Processing at the University of Edinburgh. So I've been here involved with the the program here in Edinburgh for the last year. So just graduated with that. And super excited about this opportunity in Sweden. A little bit more about me. I am married to a Swede, and so we spend a lot of time in Sweden. I've spent a lot of summers in Stockholm and in some of the surrounding areas, and we can definitely see ourselves living in Sweden. So we're really excited about this opportunity, and I'm even more excited about the opportunity to research, to dive deeper into speech technology that I'm interested in, especially with like audio ML and TTS and conversational systems. It's all very interesting and exciting to me. So I'm very much looking forward to this opportunity. So again, thank you. So as a part of this process, this video, I'm going to be discussing the paper that we have here called Voice Filter, Targeted Voice Separation by Speaker Conditioned Spectrogram Masking. And so this paper comes from researchers at IDEP Research Institute and Google, and they presented this in Inner Speech in 2019. And I chose this paper because I feel like it addresses a pretty practical problem that a lot of audio teams, at least audio teams that I've been associated with recently, have dealt with. And that is a problem that I think linguists call the cocktail party problem, when you have an audio recording and there's two or more voices, or there's noise, and there's just a lot going on in that audio voice. But trying to pick out what is most important about the audio, which part of it is part of the conversation. How do we deal with that noisy environment? And I think that historically that's a pretty difficult, hard problem to deal with. And I feel like that's very relevant to conversational systems, because if an agent is engaged in a conversation with two or more people, who should that agent be listening to and engaging with? We want to kind of avoid the instance where, because two people talked at the same time, that neither is actually listened to, and there's confusion. So for a conversational agent, I imagine that there's a few solutions that can happen. You can try to understand everyone, and that seems like the hardest option. And the second is trying to understand the most important person, or the most important information, but person in a conversational setting, in that conversation. I think that's kind of what this paper is trying, or is potentially addressing. And then third, you can maybe identify that there is a lot going on in any given audio, and then you kind of ask to kind of gracefully maybe take turns or repeat, or something like that. So that's another option, maybe in a conversational setting. But it seems appropriate to, in an engaged conversation between two parties, to kind of mask anything else that you might be listening to from the perspective of a conversational agent. So in real world scenarios, things like Google Home or Siri, virtual assistants, they have like a primary user, right? So my phone listens to me. But there's also a lot of competing sounds, background noise, and music. And I think solving this problem is one of the key steps in maybe conversational modeling, is being able to perform reliably in these dynamic environments, such as a busy household or an office or a restaurant or even the outdoors. So back to this paper, voice filter kind of specifically addresses the problem of multi-speakers by creating a system that filters everything out besides a target speaker that we're looking for. And I think, you know, like I said, conversational agent should maybe be giving attention to just one person in a conversation. So um, if we look at the title of this paper, targeted voice separation. So we know it's a targeted voice by speaker conditioned spectrogram masking. So they're using spectrogram masking, which I think is quite interesting. This system that is proposed here in this paper, it learns to mask out all the other audio to give us like a clean signal, cleaned audio. But what's interesting is that it's learning the mask. It's learning what to mask out, and it's not learning directly that clean audio, which is maybe the traditional regression problem that a lot of maybe deep learning approaches were in the past. And so this paper kind of approaches a new speaker conditioned with embeddings method to kind of target a speaker's voice. And that's where the novelty, I think, kind of lies at this time in 2019, where we're now using a reference audio and speaker embeddings to kind of guide this separation process of audio. And it's clear when reading this paper that the researchers were very focused on ASR goals and word error rate specifically. So if we look at the approach of this paper, there's kind of two systems that are talked about in this paper. And so we have a speaker encoder LSTM that takes a reference audio and it produces what's known here as a D vector. And this is trained on a very large data set with many speakers. I think in the presentation, they said tens or hundreds of thousands of speakers in the data that the embeddings are trained on. And this enables the system, or hopefully enables the system to identify and distinguish the target speaker from other speakers accurately. So the second part of the system is the actual voice filter. And so it takes a couple things. It takes a noisy audio, noisy in this case, meaning the combination of two utterances. So yeah, they have clean audio being one utterance and then noisy audio being two that are just added together, just overlaid. And so it takes this noisy spectrogram and it also takes a D vector from the reference audio from one of the speakers in the noisy audio. And because these D vectors are already very condensed representations, we kind of skip the CNN part as far as the input is concerned. So the CNN creates a more condensed representation of the input spectrogram here. And then we kind of pass it along with the D vectors through the layers of the LSTM, through some fully connected layers, and then that is to produce a mask. And that mask then is used to give us an enhanced audio, an enhanced spectrogram, here marked masked spectrogram, which is used in that loss function with the clean audio. But there's a couple of design choices here that I want to highlight, and one is the training of two separate systems. So one is the speaker encoder network, and then the other is the voice filter network. And I think end to end isn't always the answer, and so I think it's potentially beneficial here to have two different systems, one being the speaker encoder and one being the voice filter. There are two completely different tasks that can be learned very well separately. So more to do with the setup. So we have these training triplets that we kind of talked about before, where we have a reference audio and clean audio from speaker A, and then the noisy audio is A plus B, speaker A plus speaker B, overlaid on top of each other. And so these triplets are used to use the reference audio to get a D vector, noisy audio to get our enhanced audio, and then the training happens by comparing it to that clean audio. So the data sets that were used specifically in the training are, they use LibreSpeech and VCTK. And then metrics that they used are specifically word error rate. So we see down here, word error rate and source to distortion ratio. So as far as the results of this paper, first of all, the noisy word error rate is significantly reduced by this voice filter. So we drop from 55.9 to 23.4% from the word error rate with a bidirectional LSTM. So as you can see, they tried with a couple of different versions of the LSTM. Another thing to note is that the system on the clean word error rate is about the same. It's close to the same, meaning that it didn't reduce performance. It didn't negatively impact the clean audio. So it's not filtering out the important bits. The other metric, the source to distortion ratio, kind of shares that same finding, that the voice filter helps in the noisy word error rate, doesn't so much affect the clean. Sorry, not word error rate, but the source to distortion ratio. It improves with the implementation of the voice filter system. And so the best results come from the bidirectional LSTM, and that tends to make sense because bidirectional LSTMs have those two directions from which they can draw contextual information. And bidirectional context has seemed to help a lot in a lot of audio problems in audio processing and such. And yeah. So as far as strengths of this paper, I think that there's a practical applicability of this paper. The researchers, I think, point out in here that it's great to require no prior knowledge about the number of speakers that are in a given audio, and directly target the speaker that we want to have the clean audio for. And that, I think, is highly useful in a lot of real-world applications like personal assistants or automated transcriptions in noisy environments and classrooms and such. I think this paper produces some promising results as far as having a significant reduction of word error rate in noisy situations. I think there's still a sizable word error rate, so it's certainly not perfect. But generally, this paper is very easy to read, easy to understand, easy to follow, clear-ish diagrams and metrics. A couple of limitations that I want to highlight. I think data is always a limitation. The two data sets that were used to train this, the VCTK and the LibreSpeech, they're both read speech data sets. And with applications of this kind of voice filter, I really see it, especially in the context of conversational agents. I think spontaneous speech makes a lot more sense. So I would love to see these results kind of matched or improved or experimented with on more diverse data sets where there's more spontaneous speech, there's more found data. The authors in here claim that the acoustic quality of the original audios is slightly improved because of the voice filter. And I don't think that claim is significantly backed up with evidence, just because the word error rate on clean processed audio with the voice filter is slightly lower. I just don't think that it's a claim that is provable. at least from what the information we have here. And there's some kind of overconfidence. I think the authors seem to kind of paint an idea in their discussion that this problem of audio separation seems to be kind of solved. What we need to do is more fine tuning and hyperparameter sweeping, and lowering computational costs, and but that's about it. And I think that's kind of a wrong approach. I don't think there's much to merit that kind of confidence. So a couple of extensions that I see that I think could be really great additions to a body of research like this is, first of all, really understanding seen and unseen speakers. I have no idea, based off of this paper, this reading, the presentation from InterSpeech, what speakers were used to train that speaker encoder. Um, you know, the whole purpose of something like this is to be able to be generalizable. And it would be interesting to know how robust the system was to those speaker embeddings, because if the speakers in the VCTK and the LibreSpeech dataset were also included in the training of the speaker embedding model, then it could be potentially flawed as far as generalizability to unseen speakers. And so I would be interested, in addition to that, I'd be interested to experiment with maybe a larger noisy data set. This paper is very reduced and narrow in its definition of noisy, meaning that it's just two utterances together. So, what happens when you have speakers with speaker embeddings that are close? What happens when you have more than two speakers? What happens if you're in a noisy environment? I think as far as real world application and testing, like, do accents, different types of speech, different ways things are said, prosody, ways of saying utterances, do any of those things break the system where the word error rate doesn't improve? I think breaking a system is a good way of understanding it. And so I would be curious as to know how many speakers simultaneously speaking. At what point does the masking start to break down? My guess is it's pretty soon after the two, but it'd be interesting to know. And another thing we could do is kind of throw a more modern architecture, right? We could throw transformers at this and then see what self-attention can do as far as modeling this voice filter kind of problem. So in conclusion, I think this paper is a really interesting way for systems to pay attention to just one speaker. I think it's a seemingly versatile and kind of promising research that has a lot of real world application. I think it could also help conversational systems kind of navigate this cocktail party problem of multiple speakers, of who do we focus on, and really just try to focus on that and be very dynamic. And I think ultimately the overall goal is to be more graceful in addressing these turns as you're taking turns in a conversation. Like, how do we gracefully address these things while retaining system understanding? And one problem that I just observe in the space of conversational AI is that many things are important to a conversation. There's back channel identification, there's breath identification, there's prosodic context, and there are so many solutions which undoubtedly improve like one specific aspect of this conversation in very specific limited circumstances. And it's really difficult for all these systems to like work together, maybe more similarly to how we approach conversations with all of these things going on, all of these processes going on simultaneously. I would like to end there and really just, I really appreciate the consideration for this program, for this position. I understand how much work that means that we'll do together. And I would be honored to be able to speak with KTH further. Thank you.